This small piece of metal could be the most dangerous connection in your electrical installation. It's called a cable lug. You'll find them on switchgear, transformers, motor drives and high power distribution boards carrying hundreds, sometimes thousands of amps. And yet many people treat them like a simple bit of hardware you just crimp onto the end of a cable. But here's the problem. Cable lugs are anything but simple. Different cable constructions, conductor classes, crimp profiles, tooling systems and international standards all have to line up perfectly. Get it right and you create a connection that can last for decades. Get it wrong and the result can be overheating, equipment failure or even fire. At first glance, cable lugs all look pretty similar. Just a metal tube with a barrel for the conductor and a flat palm with a bolt hole to connect onto equipment like transformers, switchgear and motor drives. They come in a huge range of sizes, designed to handle everything from modest currents to the very highest power levels in electrical installations. At its simplest, the job of a cable lug is to connect a cable to a piece of electrical equipment. The barrel is crimped onto the conductor, compressing the strands together to form a solid electrical joint, and the palm allows that connection to be securely bolted onto the terminal of the equipment. In other words, the cable lug acts as the bridge between the flexible world of cables and the rigid terminals of electrical equipment. But despite looking simple, these connectors are anything but. Every part of the system has to match correctly for the connection to perform safely under load. So in this video, we're going to break down everything electricians need to know about cable lugs. We'll look at the different types of cable lug, how they're manufactured, the crimp profiles used to connect them, and the mistakes that can turn a simple connection into a serious problem. Because once you understand how cable lugs really work, you'll never look at this small piece of metal the same way again. So if cable lugs play such an important role in high power electrical systems, the next question is, how are they actually made? Because although they look simple, a lot of engineering goes into this small component. Most cable lugs used in electrical installations are made from high purity electrolytic copper. Copper is chosen because it offers excellent electrical conductivity while still being soft enough to deform properly during crimping. The manufacturing process usually starts with a copper tube. From that tube, the lug is pressed and formed into shape. One end becomes the barrel where the conductor will be inserted. The other end is flattened to create the palm, and a hole is punched through so the lug can be bolted onto equipment terminals or bus bars. Once the lug has been formed, it goes through an annealing process. This heat treatment relieves the stresses created during forming and softens the copper, making it far less likely to crack when high crimping forces are applied. After annealing, the lugs are typically tin plated. That thin coating of tin helps protect the copper from corrosion and ensures a reliable contact surface when the lug is bolted onto a terminal. So while a cable lug might look like a simple piece of metal, it's actually a carefully manufactured component designed to deform in a very controlled way during crimping. And that deformation is exactly what creates the electrical and mechanical connection between the cable and the equipment. Of course, manufacturing a cable lug is only part of the story. For these connections to work safely in high-power electrical systems, they also need to follow strict technical standards. One of the most widely recognized is the DIN compression cable lug, defined in DIN 46235. These lugs are very tightly specified. The standard defines the dimensions of the lug, including the barrel length, palm thickness, and bolt hole size. It also defines the conductor cross sections the lug is designed for, and these lugs can be used with single, multi-stranded, and fine-stranded conductors. But the standard goes even further than that, and if you look closely at a DIN lug, you'll see markings stamped along the barrel. These markings identify the conductor size and bolt size, but they also indicate the number of crimps required and where those crimps should be placed. So when the correct die and crimping tool are used, the installer knows exactly how many compression operations are needed and where to apply them. This level of definition helps ensure the connection can be installed consistently and repeatably. The downside is that DIN lugs tend to use more copper, which can make them more expensive, and their larger standardized dimensions can sometimes make them too bulky for compact equipment or confined installation spaces. But DIN is only one approach to achieving a reliable crimped connection. Alongside DIN compression lugs, another design is widely used in electrical installations, the tubular cable lug. At first glance, they look very similar to DIN compression lugs, but there are some important differences. Tubular lugs are typically shorter, and their barrel dimensions are defined by the manufacturer rather than the DIN standard. Because they use less copper, they are generally more cost effective, which is one reason they are so widely used. Unlike DIN lugs, tubular lugs don't usually have crimp positions stamped onto the barrel. Instead, the correct number of crimps and the crimping profile are defined by the manufacturer's crimping system. In these systems, the cable lug, the crimping dies, and the crimping tool are designed and tested together. That means the performance of the connection depends on using the correct combination of components from that system. It also means installers need to pay careful attention to matching the lug to the conductor type. For example, some manufacturers produce special cable lugs for fine stranded conductors. These lugs typically have a slightly larger barrel dimension to accommodate the flexibility of fine stranded conductors, and often feature a fluted entry that makes it easier to insert the conductor without damaging the strands. You'll also see other variations depending on the applications. Some lugs are designed with reduced palms, allowing them to fit onto compact switchgear or terminals where space is limited. In other regions, installers prefer lugs with an inspection window in the barrel, which allows you to visually confirm that the conductor has been fully inserted before crimping. All of these variations form part of the manufacturer's system design, ensuring the lug is suited to the conductor and the installation environment. Regardless of whether the lug follows a DIN dimensional standard or a manufacturer-defined crimping system, what ultimately matters is how the connection performs once it's installed. That's where the International Performance Standard IEC 61238-1 comes in. This standard verifies that cable lugs and connectors can survive the kinds of stresses they will experience in real electrical systems. For example, connectors are subjected to mechanical pull-out tests where force is applied to ensure the conductor cannot be pulled out of the lug. And this is the exact cable you've just seen in that test. And the interesting thing is, the crimp is so strong, it wasn't that failed. It's the individual strands of the conductor that have actually started to snap. They are also put through thermal cycling tests where current is passed through the connection repeatedly, heating it up and cooling it down hundreds of times to simulate years of operation in service. And for high power applications, connectors may also undergo short circuit current testing where extremely high currents are applied for a very short time. If the connection maintains stable electrical resistance and mechanical integrity, it passes the test. Now, to the untrained eye, all cable lugs appear similar, especially when you're selecting based on the size of the bolt hole to fix to the equipment and the cable conductor size that you're fixing to as well. But there, of course, are ways to cut corners, and you may be tempted to choose a cheaper lug. And manufacturers can skimp on a few things, such as that annealing process to ensure that the lug deforms in the correct way and doesn't split or crack when it's crimped. Or perhaps you just focus in on the really expensive part, and that is the amount of copper. So in this bag here I have 10 Klauke lugs for a 10mm cable and an M8 bolt, and they weigh in at 61 grams. Very good. Now, I bought these on an online retailer, again for 10mm cable and an 8mm bolt size, and they weigh in at a not so impressive 32 grams, so half the amount of copper. So whether you are using a DIN-defined lug or a manufacturer's crimping system, the goal is the same, a connection that performs reliably and safely under load. Which brings us to the most critical part of the whole process, the crimp itself. Because regardless of the lug design, the quality of the connection ultimately depends on how the conductor and the lug are compressed together. Over the years, a number of different crimp profiles have been developed, each designed to apply pressure to the lug barrel in a particular way. You'll see types such as indent crimps, hexagonal crimps, quad point crimps, and notch crimps. But in modern electrical installations, two methods are used most frequently: hexagonal crimping and indent crimping. Hexagonal crimping uses a six-sided die to compress the lug evenly around the conductor. As the die closes, the barrel of the lug is deformed uniformly, forcing the copper tightly around the conductor strands. To achieve the correct compression, hex crimping uses interchangeable dies. Each die is matched to a specific conductor cross-section and lug size, so selecting the correct die is essential. These dies are typically used in manual or battery-powered crimping tools, which apply the high forces needed to deform the copper. Hexagonal crimping produces very consistent compression and is widely used for larger power cable lugs, particularly in DIN systems. Indent crimping works slightly differently. Instead of compressing the entire barrel, the tool forms one or more deep indentations in the lug. These indentations push the conductor strands tightly against the inside of the barrel, creating a secure electrical and mechanical connection. Some indent systems also use interchangeable dies, but many modern crimping tools use die-less crimping heads. These automatically adjust to the conductor size, allowing installers to crimp a range of cable sizes without changing dies. This can make indent systems particularly convenient for site work where multiple cable sizes are involved. But regardless of the crimp profile used, the goal is always the same: to compress the conductor and the lug so tightly together that they behave almost like a single piece of metal. When the crimping tool applies pressure, the copper barrel and the conductor strands plastically deform. This forces the metal surfaces into very close contact, reducing the air gaps between strands. At these high pressures, the copper surfaces begin to bond together at a microscopic level, a process often described as cold welding. The result is a very low resistance electrical connection with strong mechanical retention. In effect, the conductor strands and the lug are compressed into a solid mass of copper. It's worth understanding the basic process for making a crimped connection. For tubular cable lugs, the manufacturer's data will normally specify the number of crimping operations required. This depends on the size of the lug and the size of the die being used. The first step is to select the correct size of die for the lug and the cable cross-section. Using the correct die ensures the crimping tool applies the right amount of compression to deform the lug and conductor properly. Preparing the cable correctly is also important. The conductor should be stripped to the depth of the crimp barrel, plus around 10%. That extra length allows for the fact that during crimping the lug will stretch slightly as the copper deforms. Once the conductor is fully inserted into the barrel, the crimping operation can begin. With hexagonal crimping, the first crimp is made furthest away from the cable entry, near the palm of the lug. The remaining crimps are then applied progressively back towards the cable, spacing them evenly along the barrel. This ensures the compression is distributed along the lug and the conductor is held securely throughout the crimped section. The process for indent crimping is very similar. Once the conductor is fully inserted into the lug, the crimping operation can begin. When multiple indent crimps are specified, it's usually best to apply them on alternate sides of the barrel. This helps distribute the compression more evenly and prevents the lug from bending slightly during the crimping process. In both cases, the aim is to ensure the conductor is securely compressed along the length of the barrel, producing a strong electrical and mechanical connection. Of course, that's how the process should work. And when the correct lug, die, and crimping tool are used together, it's actually quite easy to produce repeatable, high-quality crimps using a system approach. But start mixing things up, the wrong lug, the wrong die, or the wrong tooling, and problems can quickly start to appear. All of the crimps you can see on screen have something wrong with them. So let's take a closer look. First up is under crimping. In this example, the wrong size die has been used, meaning the lug has not been compressed sufficiently. The result is a loose connection where the conductor can easily slip out of the lug. These kinds of mistakes are usually quite easy to spot because during the crimping process, the size of the die is stamped into the side of the lug. That is, until someone files the wings off the lug and covers it with heat shrink, making the problem much harder to detect. Next we have over crimping. Here a die that is too small has been used. In this case, a 185 square millimeter die applied to a 240 square millimeter cable and lug in both R series and DIN versions. The excessive compression forces extra copper out from the sides of the barrel, forming what are often called wings. At first glance, this might appear to be a very firm connection, but applying too much pressure can actually damage the conductor. The extreme deformation can break individual strands, and the stretching effect can reduce the effective cross-section of the conductor. This can lead to increased resistance and heat buildup under load. In this next example, we have a DIN lug. The marking on the barrel shows that 3 crimps are required for this size of lug when using this crimping system. But only 2 crimps have been applied, and they're also in the wrong locations along the barrel. This means the compression isn't distributed properly along the conductor and the lug. This DIN crimp also looks slightly different from the ones that we've shown so far. That's because it's designed for a special purpose: connecting aluminium conductors. Aluminium should never be joined directly to copper. When different metals are in contact, particularly in the presence of moisture, galvanic corrosion can occur, gradually degrading the connection. To prevent this, special aluminium to copper lugs are used. These typically contain a compound that excludes air and moisture from the crimped connection, and they can be crimped in the same way as standard DIN lugs. Using standard copper lugs with aluminium conductors is a surprisingly common mistake on site. At first, the crimp can appear mechanically sound and electrically acceptable, but over time the joint can deteriorate, eventually leading to increased resistance, overheating and equipment failure. Incorrect crimp position. This one's simple. The crimp is in the wrong place. It's been applied too close to the shoulder where the barrel meets the palm. That part of the lug isn't designed to be crimped. Instead of compressing the conductor, you're distorting the lug. The result? Less grip on the conductor, poor compression where it matters, and a connection that's weaker than it looks. On site, many of these faults disappear under tape or heat shrink, but they haven't gone away. They're just waiting, and it might take months or even years before they show themselves.
Now, all the mistakes you've just seen were made using the manufacturer's lugs and the manufacturer's crimping dies as part of a system, so it's possible to make mistakes even when you have everything from one source. But now let's throw in the lug with less copper that we saw earlier on. I'm going to take a crimp tool, which has got the exact die for what we think is a 10mm lug, but that's a Klauke 10mm lug. So I'm going to take our very competitively priced one. It's suitable for 10mm cable. Straight away we can see we have an under crimp. It doesn't crimp to the right size. We're in the field, we've got a job to do. The next option we do is possibly drop down a size of crimp die. So instead of using the 10mm, we opt for the 6. It's certainly crimped, but you can see we've ended up with the famous wings. But then we take the correct components for this with the right lug and the right die, and we get the crimp that we're looking for.
Throughout this video, we've focused mainly on connections between cables and equipment using crimp lugs, as that's the most common application. But cable lugs are also used to join cables together, forming reliable inline connections. Most cable lugs are made from copper due to its excellent electrical conductivity. However, you'll also find lugs made from specialist materials for more demanding environments. For example, stainless steel lugs are used in marine or corrosive environments where resistance to corrosion is critical, and lugs made from nickel are used in high temperature applications where they can withstand temperatures of up to around 650 degrees Celsius. Cable lugs might be one of the cheapest components in a high current installation, but get them wrong and the consequences can be anything but small. Get them right and you've got a connection that will perform reliably for decades. If you want to test what you've learned, head over to our training portal, take the quiz and grab your free CPD certificate. And remember, it's not just about the lug, it's about using the right system, the right lug, the right tooling and the right knowledge. You'll find links in the description to the Klauke range of cable lugs and crimping tools. And if you want to go one step further, another related component to cable lugs are cable ferrules. They come with similar challenges but very different requirements. You can learn more in our complete guide to cable ferrules, which is on screen now.